Good day. It's my pleasure to welcome you to this video presentation as part of the IPC Thought Leaders program. My name is Franz. The title of this video is Electronic Materials, Vectors to Circles. The main focus of my remarks is the stuff our products are made of, which I'm calling electronic materials. A vector, of course, is a quantity having both direction and magnitude. This concept seems fitting for today's electronics, since we as an industry are moving rapidly and increasing the amount of our impact at the same time. The circle refers to a more holistic rather than a one-way flow of materials, which I believe is and must be our future. It is hoped you'll take away something new about the following points, as well as review of topics that may already be familiar. First, a very brief history of electronics to show how we have arrived at the present. Second, how to recognize successes and best practices to date. Third, how the momentum will continue to carry us forward. Finally, the author's vision of the future for electronic materials in the world we live in. You will be able to easily read my thoughts. They are identified by the little dreamer guy icon. Just a few decades ago, electronics was limited to telegraph, telephone, radio, and TV, computers that all ran on vacuum tubes. Gasoline cars had a very limited electrical content. Following the invention of the transistor in the late 40s, solid-state electronics grew explosively. Now, familiar devices like TVs, personal computers, and mobile phones number in the billions and outnumber the world's human population. Electronic devices are everywhere. Stepping back a bit more in history, just a couple of centuries ago, the first industrial revolution began, based on machines and the steam engine. These revolutions continued to add electricity, mass production, automation, and computers to bring us to the cyber age. We are now well on our way to the next revolution, characterized by some of the buzzwords you see on the right. We'll work our way down to the bottom of that list to sustainability. Meanwhile, the uncontrolled use of too many materials ending up in the wrong place became a problem. Pollution was a new word, as was the concept of best available technology to treat, or better yet, avoid pollution. Electronics itself could not escape the problem for very long either, due to rapid product obsolescence and old equipment piling up. Discarded electronic goods contained both valuable materials as well as some that were toxic. Enter the term waste electrical and electronic equipment, or WE. These are a few examples of the literature that began to develop in response. Of particular note is the 1987 United Nations report, which first defined sustainability. Later on, I will ask if we are making the best use of our knowledge we have gathered so far. This is a very short list of the selected regulations, including those that directly impact electronics goods. The list of regulations impacting our industry and our supply chains is huge, international in nature, and growing. But enough history. Let's see some examples of success and what we have learned about best practices. A couple of decades ago, the ROS Directive, or you may say RoHS, created a kind of lead-free revolution for many international companies, including those making high-volume consumer products. One benefit was some 1,000-fold reduction of lead, a known neurotoxin, in solder. The IPC Joint Standard 020 greatly contributed to the success of this change by mitigating moisture-sensitive component failure called popcorning. Other critical industries like aerospace are still at work addressing the reliability of lead-free products. The familiar 3 R's apply to consumer goods like packaging as well as electronics. Smaller and lighter products tend to use less material, which is good. But on the other hand, more and more substances are used, as we shall show in a moment. Reuse of some products or modules has been realized, but often the underlying technology has made it difficult to extend the useful product life very long. Successful adoption of USB chargers that can be used on multiple devices help to reduce WE. Energy-wise, leaving a transformer plugged into the wall could consume a crazy amount of energy in a year, even when not used to charge anything. 2 successes in one. Progress has been made in collecting and separating many types of end-of-life electronics products. The industry developed reverse supply chains to process WE into recoverable fractions similar to those shown here. Can this trend continue to be improved? One of the key developments from a scientific and modeling point of view has been tools to perform life cycle assessment, or LCA. These allow not only electronics manufacturers but others to quantify the impacts from raw material extraction through manufacturing, distribution, and use. An electrical device or vehicle will of course consume energy, items like furniture generally not. In fact, the charger example just shown was highlighted by LCA, where the use phase over time could consume more energy than making the unit in the first place. Finally, can the material cycle be closed, or will there be some waste? What impacts and opportunities could LCA find in your product's life? The basic principles of so-called green chemistry, as well as applied principles of green engineering, have been published for some time now. I won't read all the points here, but encourage you to stop on this slide later and review them. They actually are common sense, but of course, any engineer knows they're more easily said than done. Small steps will lead to larger ones. The foundation of improvement is measurement and the availability of standardized metrics for doing so. You may know about these product certifications like the IEEE 1680 series for computer and related equipment, which includes criteria for substance management, material selection, design for end of life, product longevity, life cycle extension, life cycle assessment, and end of life management. Energy Star covers energy efficiency for the various products shown. We also have international and European standards for all these aspects of energy-related products, which of course includes electronics. Again, I will not read the list, but hopefully we'll consider where you are taking advantage of their existence to assess and improve your own products. More standards. This series is a little more general than energy-using products in the previous screen. Note that environmental labels and declarations and methods for LCA are included. The scope of some of these is at enterprise level for environmental management. Again, I will not read the list, so please come back later as you wish. If nothing else, remember ISO 14000. Not to be overlooked in the context of electronic materials is industry's ability to report material content up to the supply chain. I can personally endorse the IPC 1752 standard and only hope that you make use of whichever format suits your operations, then take action as indicated by the data. What substances are regulated, valuable, in short supply, and so on. The REACH directive is interesting because the substances of very high concern, now numbering over 200 of them, can still be used in shipping products, but you will need to report them if entering EU member states. Some have become further restricted under ROHS. This pattern should provide a heads up to avoid designing these substances into new products, if at all possible. I did not invent this, nor in fact did the European regulators themselves, since the concept has been around for decades. But the Action Plan and Green Deal are names that are gathering traction. Will the EU continue to lead these initiatives? Given this background, next I propose to break down some barriers and speculate where all of this is taking us, and should be taking us in the near future. The best way to protect the future is to create it. The table on the left and colored elements in the periodic tables on the right show how more and more substances are being designed into electronics, having risen to more than half of the naturally occurring elements. It will take broad collaboration to address this trend. I love the example of one of the original industrial ecology texts focusing on a few widely used materials. This kind of study and reporting needs to be continued to all the substances we use in electronics. It seems we now have some very good regional capability, again in the EU, for closed-loop treatment of copper and precious metals, enforced by standards. Can we deploy similar practices elsewhere? Some of the metals drive their own recovery due to their economic value, others not so much. We have tremendous need and opportunity to roll out best available technology for the remaining 50-plus elements to ensure their recovery as well. Two trends further magnify the material picture. One is the electrification of vehicles, which of course ship in very high volume. On the right side, the highlighted elements are deemed to be critical for electrical energy generation and storage. Can these innovations be realized with other approaches that are not so demanding on so many different resources? One possibility on the horizon is the development of electronics using a familiar and abundant element, carbon, specifically when made into nanotechnology. Considerable R&D is in process to develop new devices that perform even better than silicon-based devices at the mature end of Moore's Law. The little guy on this page is thinking C. Yes, indeed. Personally, I love out-of-the-box approaches like this. Instead of pursuing more and more exotic materials, can we use existing abundant materials in new ways? The table on the right lists a few of which are mostly abundant, no high toxic effects are present compared to some elements, and they can be combined with good old oxygen to make novel ceramics. The ubiquitous element strategy aims to achieve novel and or useful functionalities which have only been found in rare and or harmful elements, with a restriction in selecting abundant and non-toxic elements for materials design. Cool. Of course, the bread and butter of electronics is devices on circuit boards. While PCB technology continues to improve in many aspects, as you'll hear from other authors in this series, what if the electronics could be printed directly? There are just two of the many journal papers shown here of the numerous articles on additive manufacturing and 3D printing. Could we be entering an inflection point? Stay tuned. Can we possibly have it both ways? Continue to use and manage the life cycle of certain materials like my favorite heavy metal lead, while at the same time continuing R&D to either substitute it, which is not easy, or find totally new materials to eliminate the need for lead altogether. Of note here are the EU organization Lead Matters and the advocacy work underway at IPC. Last thought before we wrap up. The general theory is largely there. The regulations and standards are there. Can we get ahead of the curve and understand the material impacts of new products before they are shipped in high volume? Again, I realize it's easier said than done, but this is the challenge. Let us wrap up. What would be my crystal ball telling me about what could be in place in 20 years? My vision is this. Product life cycles are extended to reduce waste. Standards are used to measure and improve, and material flows are wrapped into a loop. Common substances begin to be used to reverse the trend toward more exotic and rare materials. Energy efficiency of electronics continues to be improved. The promise of renewable energy and reduction in atmospheric carbon dioxide are imperatives that will require electronics for success. Can industry get ahead of the reactive mode for regulated substances to minimize or even stop the need for regulations later on? Can best available technology continue to evolve with more coverage and efficiency than today? Here's my dream. Working relationships are in place between international and local governments, companies, industry associations, non-governmental organizations, R&D, and education to enable the next vector of Industry 6.0, the first age of sustainability, with electronics in the forefront. A dream, for sure, but they allowed me to say it. This is all about vision, innovation, and change, building on the vectors that brought us this far. Electronics is well suited for change because it has powered change since the very beginning. There you have it, electronic materials, vectors to circles. Thank you very much.